Okay. So this is what we talked about, right? As the question was raised empirically, the experimental data, that is when you make the measurements using Ornstein-Zernicka plot from the intercept, you can get chi. The temperature difference looks like this. So if you want to have this kind of a behavior, then chi as a function of temperature or 1 over temperature should look like this big U shape. If you have this for larger values of chi, that is high temperatures, you'll have LCST. For low temperatures, T is small here, for higher values of chi, you'll have UCST. That's all, right? It's everything is possible depending upon this one. So now let me, so far what I did, perhaps I could summarize is this. So far what I showed was in this usual Flory-Huggins theory for UCST system, chi as a function of volume fraction would look like this. This is coexistence curve, and that red is a spinodal curve. Since a chi is inversely proportional to temperature, that is for the case where A is small, C is small. In that particular situation, this number C is tiny, so therefore it's not important. A is also tiny, but it's dominated by this term, B over T. That is, right, B over T, right? That is our U. This is when I plot chi versus 1 over T, it's a straight line. B is positive and it's a straight line. That's that stuff. And then you will have UCST. For that particular case, temperature, same, this figure, same as the temperature versus volume fraction. The green curve is coexistence curve and red is the spinodal curve. So you bring your homogeneous solution, polymer blend, polymer solution, small molecular mixture, whatever your system is, it's homogeneous. When you lower the temperature in this scenario, it will undergo phase separation. And the place where the spinodal curve and the coexistence curve meet is a critical point. That critical point is called a second order phase transition. Okay, this is a second order phase transition. But if you lower the temperature in this way, that is off quench, instead of decreasing temperature along this point, along the critical point, suppose I quench it off way, that is on the other side of the critical point, on the lower concentration side or a higher concentration side, off quench like this or off quench like this, then it undergoes a first order phase transition because you have the liquid phase here, one homogeneous phase here. When you bring it here, it, as a matter of time, in due course, it will undergo phase separation to give you two phases. That's the first order phase transition. So although I have the coexistence curve, you have both the critical point, which is second order phase transition, and for off critical quenches, you have first order phase transitions. Okay, this is a universal. We see this all the time. And when you reach the spinodal curve, the scattered intensity diverges, right? It goes to a very large number. And that's how we determine this A, right? And I'm repeating myself, A is temperature minus the spinodal temperature, right? That's the distance. That's the distance of temperature from the spinodal temperature. At the critical point, as you know, the spinodal temperature is same as the critical temperature. So A at the critical point, or for critical quench, A is a T minus TC. TC corresponding to the critical point, critical temperature. So this is what we did in the last lecture. And again, I wanted to mention once more. So we did fluctuations, right? There are fluctuations in the solution, the homogeneous solution. And accounting for these fluctuations, we define an order parameter, which is the value of local concentration of, say, one component with respect to the average value, equilibrium value. And that's what we define as a fluctuation. Instead of phi 2, second component, I could have defined for phi 1. Psi is equal to phi 1r minus phi 1e. It doesn't matter which component I'm talking about, right? And so that's the order parameter or fluctuation in local concentration. Using this, we did a simple Taylor series expansion to write the free energy of mixing to be of this form, right? And then A is second derivative of free energy with respect to phi 2 in this case, and therefore we got that A. And then this is the interfacial tension that is related to the penalty that we pay to create an interface. Based on this, we wrote down the free energy of mixing in the Fourier of space, where K is a scattering wave vector, which we talked about before, and K is inverse of the observational length scale. And then by defining a Fourier transform like this, right, we could write the free energy of mixing to be of this form. And from this, we got form factor, structure factor, which goes like this. And then 1 over scattering intensity is related to 1 over the structure factor. And that goes like this. This is Ornstein-Zernicka plot. From this, we got a chi parameter. And this slope gives me the correlation length of the system. Correlation length for concentration fluctuations. That is the correlation length for the concentration fluctuations here. For example, right, here the concentration is a little bit higher than average. Here the concentration of this component is higher than the average. The distance between this peak and that peak on an average sense gives me the correlation length. Okay, so that's a summary of what we did. And we are going to use this today later on. After our small break, we'll come back and use these results again. And that's one of the reasons why I am reminding you what we did in the last lecture. Now, instead of talking about the mixtures of flexible polymer chains, right? So far, we were talking about mixing chains like this and chains like that, flexible chains. This is what we did so far. Today, what I'd like to talk about is what will happen if I have semi-flexible chains, right? Or rods. Yeah, as you know, double-stranded DNA is rod-like, and there are many polymers which are rod-like. So I like to look at today a solution of rods. Solution of rod-like polymers. Say, let me take solution of rod-like polymers. Let me take a plus some solvent to give an example. Of course, you can make a blend of semi-flexible polymers with the flexible polymers. But let me take this simplistic case. So in the simplistic case, for example, imagine a rod which is going to be of length L. This length is L, length of the rod. Let's say the diameter of this rod is D. That's a diameter rod. So for the volume fraction, right, let's say let there be N rod-like molecules. In volume V. Therefore, volume fraction, polymer volume fraction, phi, you can tell this, right? Number of chains by volume, right, times volume fraction, right? A volume of each rod. This is for, there are N rods in volume V, the volume of each rod. Volume of each rod, we know length is L, D is diameter, area times, right? Area times length, that gives me volume. So that's a pi over 4 L D square. Okay, please notice that, right? Volume fraction goes like a length of this rod times a diameter square. And then there was a, you will learn from the literature, there was a great chemical physicist, great physicist, chemist. His name is Lars Onsager. And he considered this system, and he was interested in tobacco mosaic virus, how they organize. And he came with a breakthrough theory, and he said, if the volume fraction is small, the rods would be randomly oriented. But if we increase the volume fraction of the rods, he said they will undergo an arrangement of this type. This is a liquid crystalline phase, right? It's more like a crystal. There is orientationally ordered. There is orientational order. And this is called a nematic phase. Which is an example of a liquid crystalline phase. On the other hand, here is a randomly oriented. This is called isotropic phase. Right? So here is anisotropic because there is an orientation order, and here is isotropic, they're randomly oriented. So the phase diagram for this situation, what he talked about was what is called athermal. There is no energy. He considered what is called athermal. That means there are no interaction, only entropy. High temperature, only entropy, no interactions and no energy at all. Okay, for this particular case, his phase diagram looks like this because it's right. There is no axis here. There is no temperature axis here. Only volume fraction. Volume fraction would look like. Let me write down here. This is volume fraction of the rod. Once again, here is isotropic. This is isotropic. And this is nematic. And what he showed was somewhere in the middle, nothing happened. There is a phase separation. So up to this point, that point is 3.3. It's given in my handout, d over L. And this point is 4.5 d over L. Everything depends upon the aspect ratio of your rod. L is the length of the rod, d is the diameter. Right? So between this point, there is a coexistence. Just like what we had before. This is very high temperature, and below this value of 5, we have isotropic phase. Above this value of 5, we have nematic phase. And then somewhere here, between here is coexistence. That is, either it's unstable or metastable. Like what we saw before, right? What we saw before. So here, right, there is a coexistence. There's up to this is one homogeneous phase. Beyond this is a homogeneous phase. Right? Beyond this is a homogeneous phase. Below this is homogeneous phase. Then there is a phase separation. But except now instead of homogeneous phases, isotropic phases, in this particular case, we have an isotropic phase, coexisting with a nematic phase. And between this, there will be phase separation. All right? And we can generalize this calculation to thermal case, not athermal. That means there's only entropy. There is no energy at all. Then we can put in the chi parameter, right? Chi parameter has the energy part, chemical mismatch between AA, BB, and A and B, right? So if you do that, you get the following phase diagram. This was done by Flory, of course. And I have given the reference in the handout, and then you can look at that one. So if you calculate chi versus volume fraction of, say, the rod, which is 2, for example, you get the following phase diagram. Remember, go back here. right? For this case, right? For the flexible case, you have chi versus volume fraction this is a coexistence curve. Under this green curve, the system doesn't like to be stable. Either it undergoes, we'll look at the mechanisms, either it's unstable or metastable, it'll undergo phase separation. So here I have stable phase, here I have stable phase. Same thing you expect for higher values of chi. Okay. So the calculations go like the following. You get, it comes down like this, and then there's a chimney region, people call chimney region. And then it goes like that. And this phase is isotropic. Here it's isotropic. And here is nematic. Okay. And of course, here you have phase separation. And inside this, you can have spinodal curve if you like, right? There is a phase separation there. So the Onsager problem, Onsager calculations in here, because a high temperature, athermal means very high temperature. Very high temperature means chi is small, somewhere here. So these points that I'm talking about, this one is here. The one that I'm writing down here is somewhere here. At a high temperature, athermal case, I have isotropic to nematic. But if we include interactions between the segments, the phase diagram turns out to be like this. And then, as in the previous case, suppose I quench the system, right? I quench the system into this phase, in this particular condition. It will undergo phase separation. But what you will see is it will turn out to be the following. Suppose I have these rods. I'm imagining these rods. Imagine these rods are entangled, meaning they are jammed. So when I quench the system into this condition at low temperature, I'll take a solution of rods which are say isotropic here. They're randomly oriented, but the concentration is high. Suppose they quench it. Quench means I lower the temperature. I'll get into a situation of this type where the temperature is lowered, but therefore the molecules cannot move that quick, right? Therefore, what will happen is when you quench in here, the phase separation will take enormous amount of time. In order to make the phase separation very quick, it's very difficult, right? So it turns out to be very difficult. In fact, what you will get is, under these conditions, you will get a jammed gel. This results when I lower the temperature, for example, I get jamming of rods. Okay, that means very slow phase separation. In fact, you can even get, as a consequence of this, you can get gels, which we'll talk about. I would call this to be nematic gels. Right? Because it will make a gel, but it cannot phase separate. I can freeze them. It will take enormous amount of time. For all practical purposes, we could treat them to be transient networks, transient gels, but physically captured, physically entrapped nematic gels. And this is something that you should pick it up. There is a good literature, and I have given a couple of references in the handout. Please look up those references, and then from there you can go further to get deeper into liquid crystalline polymers. But if you look at many of the devices, display devices that we use, including your laptop, they use liquid crystalline polymers as a technological product. So it has fantastic technological properties. And in order to formulate them, we need to understand this phase diagram, how to process them, how to make them ordered, how to avoid this jamming. This is a huge enterprise, and it's a mature field. It's really lots of people have worked on this, and you can think about making this technology even further by combining this with other polymers, small molecular systems or block copolymers, multi-block copolymers. There are lots of opportunities to go further in this direction. So, but that's a brief description of the role of rod-like polymers. Okay, role of rod-like polymers. But here, I like to briefly point out a cautionary note. It's in the literature, you will see, right, rod-like polymers, you will see note. I'll put a cautionary note. Okay. We think that a radius gyration for rod-like polymers would go like L, which is true. Not only we think, it's true. If you calculate the radius gyration of a rod-like polymer, purely rod-like polymer, it will be proportional to the length of the rod. In fact, end-to-end distance, the square would be L squared by 12, things like that. Yeah. Excuse me, radius gyration square would be length square divided by 12, right? And end-to-end distance would be L. So therefore, we normally think in terms of overlap concentration, for example. Overlap concentration, we would write to be, right, n to the, remember this, overlap 1 minus 3 nu. Therefore, we'll write n to the minus 2 for rod-like polymers. This is not important. This quantity is not important for treating real rod-like polymers. Okay, why? I told you already, the key quantity is D over L. In order to undergo phase separation, this anisotropy of your rod-like molecule is important. And as I'm repeating myself, the volume fraction of rods, right, is not, right, it's not simply N over V times the capital N number of segments, right? You could write that way, but the important because of the physical aspect ratio, physical geometry of this rod, this is the key quantity, L times D squared. Okay, we should not simply write this to be L cubed or anything like that. Okay, but if you have a flexible chain which looks like a rod, then it's okay. Then we can use all the techniques that we used before. But if it's really a rigid rod-like polymer, then we should be cognizant of the fact it's LD squared. That's the key variable, right? Not L cubed or D cubed. Okay, that's just a note, side note. Okay, instead of this, I have to have LD squared, right? Phi goes like LD squared. This is the important quantity instead. Because this is a common mistake textbooks make in their description about rod-like polymers. Okay, now I'd like to introduce one more small topic, which is about, this is also sent to you by the, in the PDF files, I have sent it to you. But this is about block copolymers. I want to introduce very briefly what is a phase diagram for block copolymers. Okay, for the block copolymers, what I like to do is, let me be very simple-minded to give the simplistic case. Let me take two blocks, which is one is a green block, and let me call this to be A. All right. The other one is a red block. Let me call this to be B. Okay. And let's say a fraction of A this is a melt, right? There is no solvent here, no other component. It's a melt of diblock copolymers. Fraction of A would be Na. There is number of segments in the A block and NB is the number of segments in the B block, NA divided by NA plus NB. And let me also imagine that A and B are incompatible. A and B don't like each other, are incompatible. They don't like each other. Then let's imagine what will happen. If the amount of A is comparable to the amount of B, right? Then I will get something like this, right? So this is A, doesn't like B, so it'll be stretching out. But A likes A, so it'll turn out like this, turn out like this, and then this would be A. Another A likes like this. But this A is not alone, right? This is the die block. So therefore, it will happen like this, it will happen like this, it will happen like this, like that, like that. So as a consequence of this, what you get is, you get a lamellar structure. This is lamellar. So I have A block, and then of course I'll have B block. Like that. So I get a lamella. Okay. Which we'll call this to be, I'll write it down. This is a lamella. This is when they're of comparable amount. When amount of A and amount of B, this is about half. When amount of A and amount of B are comparable, that's what we will get. But on the other hand, suppose amount of A is small, FA. Okay, let me call this to be FA if you like, right? Let me call this to be fraction of A, right? FA. If FA is small, A is a minority, and then it's a common experience. If it's a minority, then the green will be surrounded by B. Then I can have situations like this. Oops. I will have, this is a minority, only small amount of A, and A likes A. This is B, this is B, this is B, this is B, this is B. And then other B's will come here, on and on. And then you'll have like this. So you'll have spheres, right? Surrounded by these spheres, spherical morphology. Here you'll have lamellae, and here you'll have spherical morphology if it's a minority. The FA is very small. But if FA is somewhere in between, this is very small and equal partnership, then you'll have cylinder morphology. Then what we'll have is you'll have like that, there is a cylinder, and then these guys will come out. And then they'll be surrounded, and then there will be another cylinder. Things like that. This will be a cylinder. These are the basics, very simple, basic morphologies. You can cylinders. Okay. So if FA is very small, you'll have spherical morphology. If FA is a little bit higher, you'll have cylinder morphology. And then if FA is about half, you'll have lamellar morphology. Suppose it goes more. If FA is, say, 90%, 0.9, then this will be reverted because now A is majority and B is a minority. Then this is exactly the same cartoon, except this is red, and then surrounding environment is green. You'll have something like this. In fact, you can calculate the phase diagram for this system using very good techniques, self-consistent field theory. If you do that, the phase diagram looks like this. This is, say, chi n. You remember for chi n, right, is for a polymer blend, flexible polymer blend, it was 2. Chi critical was 2 over n, right? That's why I'm plotting chi n. So in this scale, if it's a 2, that is a critical value of chi times n for polymer blends, flexible chains, mixture of A and B. But now you permanently connect, this is FA, right? This is FA. 1 here, 0 here. Now, once you connect them, A and B, when you hook one end of A and with the one end of B, when you get a die block, same chemistry, but I make a die block, then what happens is chi n is not, critical is not 2, but it jacks up to 10.5. Somewhere here, it turns out to be 10.5 instead of 2. That is, chi n is increased dramatically up. Then what happens to the phase diagram? The phase diagram looks like this. The phase diagram looks like it's a homogeneous. Here it's homogeneous. Below this is homogeneous. Okay. And then you get into a situation where you have, I'm going to use the same green. Right? This is a sphere. This is sphere. When I say S, that is this guy. This is S. That's a spherical morphology. Okay. Now here, green is a minority, therefore I get sphere phase. Here, red is a minority, right? Because now red is surrounded by green. Then you get into cylinder morphology, which would look like this, between here and there. This is cylinder morphology, that's cylinder morphology. So here, coming back here, I'll call this to be C, that's cylinder morphology. Then in the middle, of course, it's a lamellar morphology, capital L. So I write this to be capital L. So what we have is, this is total disorder. This is disordered phase. This is disorder here. And here order. Order with different kinds of morphologies, as an example. So it is possible for us to do, suppose I do the following experiment. I make a melt in the disordered phase, and I lower the temperature. That means I'm going to increase chi or increase the molecular weight. Then what I will have is, I'll go from here to here, from a disordered state into an ordered state. This will be called disorder-order transition. Disorder-order transition. Then once I'm there in an ordered phase, I can also do order-order transition. From sphere to cylinder I can do. Suppose I were to do, as an example, from here, so I suppose I'm here and then go there, or even go up. That would be order transition. As you know from the literature, since there are so many things we can do with disorder-order transition and order-order transition, different morphologies for different kinds of applications, the physics of block copolymers is a very active field. There is a huge literature, contemporary literature. When you take various journals, especially in polymers, you'll see lots of papers dealing with the block copolymers for various applications. But the essence of what is going on is basically contained in here. Right? Now, what I like to do is I want to show you one example of how to do a calculation, right, for measuring the domain size, the periodicity of the order structure. How do we find the average spacing between, right? This is the period, right? Because this one repeats again after, say, after here, for example. That's the period, right? This one, this interface, right? There's an interface between red and green. This is green and red, right? And then this repeats again. So let me draw a cartoon of this structure. I want to specialize as an illustration. Consider lamellar morphology. And this is a very easy calculation going back to what we did before for a Gaussian chain with the extra volume interaction. So similarly, we are going to make a very good prediction about there's a spacing. What do I mean by spacing? Let me take a lamella looking like this. Okay. And on and on. The lamella are stacked up. Okay. And when I look at, say, for this example, let me look at this one. This would be in our green and red. So here is my green, or doesn't matter. Let me follow the same color code that I have in my handout. So this is the red block, green block. Oh, sorry. Red block, red block, red block. Okay. And then there will be a green block, and then again, red block, red block, red block. And between them is there is green block, green block, green block, green block, green block, something like that. Okay. So let me write down this interface corresponds to that line, and this interface corresponds to that one, for example. Okay, basically this is a green block. And that means that the period, if this is a green block and the next one is going to be a red block, and then it'll come back again green, right? Here is that is the green, then it'll be red, then another red in here. So the period is, this is actually the period, repeating period, right? Because I have a red chain coming here from this interface, there'll be red chain, very much like this one. So I have red chain, and then a green chain, green chain. Then again, red, red, green, green, right? Therefore, the real period is D, right? And in this period, there are two interfaces, one interface like this, another interface like that, all right? There are two of them. So what I have then is, I started with, consider a block of, say, length L, and length L. There are n chains. Normally we say n chains. And it's a melt. There is no solvent, right? Therefore, the density, polymer density, rho, is equal to, you guys know, n times degree of polymerization of the die block, which is Na plus Nb. Na plus Nb is n, right? N is equal to Na plus Nb, right? Divided by volume, that's L cubed. Okay. Now, in order to figure out how capital D, the period depends on molecular weight, that N, how D depends on molecular weight, what I'm going to do is I'm going to calculate the free energy associated with the stretching of this chain, because when they are ordered, the chain is going to be stretched. And also, what is the constant free energy at the interface? Okay, that's what I'm going to do. All right. Let me take a small 1 second break. Folks, I think I want to continue this argument for 5 more minutes. Is that okay? Hello? D?
Yeah, hello? I'm here. I think it's fine.
Okay. I want to, I don't want to interrupt my argument here. So I want to calculate free energy due to interface. Right? Let's consider one interface, right? Say one interface, right? What is free energy? We know that that is equal to interfacial tension. Interfacial tension times the area. Interfacial tension times the area, right? That's the interface of free energy. What is the area of a interface? That is, this dimension is L, this dimension is L, so that area is L square. So that is surface area, L square. Surface area per one interface. Then we have to figure out how many interfaces there are, right? What is the number of interfaces? the total length is L, and the period is D. Therefore, right? Therefore, the number of interfaces would be, number of periods would be capital L divided by D. L is a total length, D is a period. So number would be capital L over D. But per period, there are two surfaces, right? Because this one repeats again. So therefore, there are only two surfaces per period. Therefore, I'll have 2, right? L over D. So this factor gives me a number of interfaces. Okay, so let's work it out. So the free energy due to interface per chain, we'll talk about one chain. Per chain, that means that's equal to 1 over n times everything. The above, right? 1 over n, there are n chains. I told you there are n chains. It's 1 over n, then sigma, okay? And there is a 2 sigma, and then L cubed divided by D. Okay, but we know what the density is. Look at this. Density is n times capital N by L cubed. So here I have L cubed by N. L cubed by N would be capital N divided by rho. Therefore, this gives me 2 sigma by rho, right, times N. And then there's also this D. There's the D in here, right? N over D. Okay. So this is a free energy of interfaces due to one chain. 2 sigma by rho is a number. The big interfacial tension depends on your chemistry. Density is your material, right? Melt, right? And then N is the degree of polymerization of your diblock copolymer, and D is the domain spacing, which we do not know yet. But we know what the free energy of stretching is. Free energy per chain for chain stretching we know that. That is, remember Gaussian chain, end-to-end distance is square divided by molecular weight, 3 kBT by L square. We did all those things, right? For the stretching case, free energy per stretching is end-to-end distance is square divided by N. So now what we have to do is we have to add these two. There is stretching free energy and the free energy cost to create interface per chain, that is that. So we minimize the free energy of this total expression that is the sum of this and this. We'll take the derivative with respect to D and we find the optimum. So let's do that. Therefore, free energy in units of kT, if you like, goes like those two quantities, right? This goes like, one goes like sigma by rho N over D, and then the other one goes like a D square by N. This is stretching, and this is interfacial energy. Interfacial free energy. We have these two, right? Therefore, dF by D is equal to 0. Then let's do this. So from this one, minus sigma over rho N over D square. And from this one, it's a plus 2D over N. This is equal to 0. And then you solve this, you get a D going like N to the 2/3. Okay. So now we have determined by a simple calculation the domain spacing of this structure. And whatever you have this one in general, the domain spacing is given by molecular weight of the diblock copolymer with this power law. This is really fantastic. You know why? Because I can make any morphology I want with the right spacing. If I want to do some lithography, if I want to do filters, if I want to make filters of a certain domain size with a certain crystal symmetry, you can tune it with this formula, right? D going like into the 2/3, for example. So, you know, by just thinking very simply, we are able to penetrate into designing materials of your goal, for your goals. I must point out, this is true in the limit of strong segregation limit, because we assumed the lamella are already formed, strong segregation limit. This is the design principle in the strong segregation limit. In the weak segregation limit, that means it is not so well organized like this, but it's more like this one. That is, it's more like that one, not well organized. And this is a weak segregation limit. In the weak segregation limit, the D basically goes like Gaussian chain, because the end-to-end distance is proportional to square root of molecular weight, and that's what you get in contrast. Okay. All right, so that's, I think, the end of a discussion of diblock copolymers. Unless we talk about kinetics of order transition, kinetics of disorder order transition later on. If you have time to do that, we'll talk about it, and then we'll come back to block copolymers or their analogs, their equivalent analogs. I think this is good enough to have some sort of background about diblock copolymers. Okay, block copolymers in general. I hope you get a flavor of how this works out. Now let's take a break. Thank you for spending extra 5 minutes. Let's take a break after 5 minutes. Is that okay?
Yeah, we have 5 minutes break.
Yeah, let's do that. I'm going to pause. Right. Maybe I'll stop here and I'll open it again. All right, I'm going to stop sharing.
Okay.
And then I'll pause the recording. Right. Now we are going into a new topic. Right. Basically, we want to understand how you get coexisting phases. I don't know why I can't see my screen. Do you guys see the screen? I'm not able to see my screen. Let me try once more. Let me stop sharing and do it again.
Oh.
Yeah, now, okay, good. So today, now from this lecture onwards, what I'm going to do is, remember, I told you about the phase separation, right? So here, oops, sorry. Right, so here is chi as a function of volume fraction, or going back to this picture, temperature as a function of volume fraction. And we talked about this theory already, right? How the fluctuations are taking place in the homogeneous phase. Then I'm going to quench it here. When I quench it, how is the phase separation going to take place? Because I told you that when I quench it, I'll go into these two coexisting phases, phi 2 prime and phi 2 double prime. And then when I quench it into the unstable state, and I below the spinodal curve, and I mentioned that we are going to do spinodal decomposition. There is a mechanism by which the phase separation is going to take place. And that's called spinodal decomposition. And the next lecture, we'll talk about quenching into metastable state, and that will undergo nucleation growth. So now for the next 30 minutes, I'm going to talk about this mechanism of spinodal decomposition. Okay, so that's my goal. Okay, again, once more, let me draw this again. So our goal here is phase separation kinetics. And I say part one. And I call this to be the mechanism of spinodal decomposition. Okay, let's go to our picture again once more. Right, this is the temperature. I'm illustrating with the UCSD system, and this is my volume fraction of the polymer, and you know this coexistence curve, and you know the spinodal curve. Now what I'm going to do is I'm going to take the system here in the homogeneous phase. I'm going to come down here. Right, I start from here, homogeneous phase, and then I quench the system to at low temperature. I come here, and as you know, this is going to as a function of time, and this is going to phase separate to give me one phase which is phi prime, another phase which is phi double prime. And I'm going to illustrate this with, in general, component 1. Okay. So the way it happens here is when you quench the system in here, there is a spontaneous fluctuation. Leads to the spontaneous fluctuation. The system, when it's quenched into an unstable, so this is an unstable. Remember, we went through this again and again. This is unstable region, right? This is no. This is not allowed. So when it changes, when you quench a system into an unstable state, it undergoes a spontaneous fluctuation. The situation undergoes spontaneous fluctuation. That means what? That means you can write, for example, as we talked about before, right? Your local volume fraction phi at some location R at time t is equal to some equilibrium value. Doesn't matter whether it's component 1 or component 2. I'm not going to write the subscript. Take any component, say 1, all right? Phi, that's the equilibrium value, plus the fluctuation quantity psi at RT. And we drew a cartoon like this, right? This is phi RT would go like this. This is a kind of R, right? Spatial location. And this is a phi RT, right? And there is an average value, which is a phi E. And we talked about the fluctuating quantity. All right? We talked about this is a fluctuation, psi RT. So this is my fluctuation. This is my psi RT. That's a fluctuation. This is a fluctuation. Let's just imagine how this can happen, because already even in the homogeneous phase, there is some fluctuation. That's how you determine your chi parameter, by monitoring what the fluctuations are. But when I quench it here, eventually as a function, you start like this at t is equal to 0, because you are like this and quench it. At t is equal to 0, it looks like this, right? And then as the time is clicking by, it undergoes phase separation. Then what you have is, you have two phases. One phase is here, another phase is here. So the concentration profile is not like that. Instead, the concentration profile is going to be more like this. It will be one phase for goes over, and then the interface, and then the other phase. So this is my axis R modulus, and this is my phi, right? This number is phi double prime, and this is a phi prime. Because eventually there will be one phase corresponding to that phi prime, and then there's an interface, and this is another phase at phi double prime, which is a macroscopic. This is macroscopic phase, this is macroscopic phase. Somehow the spontaneous fluctuations, which look like this, have to evolve eventually into this case. So let's draw a cartoon. And what do we expect? To begin with, right? And the molecules are like this, some fluctuations. And when I increase the time tiny bit, right? Then what will happen is you'll have something like this. There will be fluctuation. There will be some domains which are more in concentration, another domains which are less in concentration, and more in concentration, and less, something like this, more in concentration, less like that. That's what we call fluctuations. And eventually, of course, we'll have here all very high, right? That is 5 to 5 prime, double prime, and then less dense. That is your 5 prime. Okay, that's what is going to happen. So again, time is clicking. To begin with, there is some weak fluctuation. That's how I prepare my system, and the fluctuations will grow. And then locally, the fluctuation is strong here, and eventually I'll have 2 macroscopic phases. And how do we describe this? All right, this mechanism by which spontaneous fluctuations grow to make the macroscopic phases is called spinodal decomposition. Okay, that's the name of this. So I'm going to describe this in very simple-minded fashion. Just taking mass balance, if I take some location and look at the time evolution of a local concentration, d by dt of a phi is concentration of one component. You could choose anything that you like at time t. But this is given by how much material which are coming into that volume. Okay, and that is given by this quantity. This is divergence, gradient in 3-dimensional space, and this is called flux. This is called flux, and you know gradient. This is continuity. This is mass balance. This is mass balance, or in your undergraduate program, you'll know this is called a continuity equation. And what is a flux? This flux, J, is written by, again, thanks to this gentleman, whose name I already mentioned. This is called Onsager coefficient. The meaning of this lambda, I'll write other terms. Meaning of lambda is mobility. How the molecules are able to move around. And of course, it's dictated by gradient in chemical potential. Remember, we talked about it. In order for molecules to move from a non-equilibrium state into an equilibrium state is through negotiating the gradient in chemical potential. Eventually, the chemical potential gradient should vanish. Until that, there will be a flux. Okay, this is the mu is chemical potential in units of kT. Right. The mobility is related to the diffusion coefficient, which we'll talk about when we talk about dynamics of polymers later on, maybe 3 lectures down. Right, it's related to the diffusion coefficient. We'll come back to that. So basically, we have the time evolution of the constant local concentration is given by negative del dot, and then another sign, negative times negative positive, lambda comes here, del square, del here, another del square, and chemical potential. What is chemical potential? You know that. The chemical potential, mu by kT, mu in general, is proportional to the first derivative, delta Fm by d phi. We know we have an expression for blends, solutions, there's free energy mixing, and we can take the first derivative of that, then we'll get chemical potential. And there's a proportionally constant you can work out. You know that d delta Fm by d little n1, number of chains of type 1, etc., etc. You know the formula. But in general, for that component, chemical potential is proportional to the first derivative of delta Fm with respect to its concentration. So if I know this, put this in here, and then take the derivatives in here and operate, and then that gives me time evolution of the local fluctuation. But now I'm not into, well, what do? I measure experimentally only the fluctuations, right? It's difficult to measure the concentration. Then you have to do chemical analysis locally. How do you do that? That's very hard to do, right? What do you measure is the fluctuations. And fluctuations I have defined already. the fluctuation is whether the phi of RT is equal to equilibrium value, which is a constant, because you know the composition, plus the fluctuation. I take this equation, put this back in here, and I do these things, right? If you do this, you get the following results, okay? And also I want to tell you in scattering experiments, you use in terms of scattering wave vector, right? That's how you measure. Therefore, we use Fourier transforms. Let me define psi, the fluctuation at some location RT, in terms of Fourier variables k, psi k here, e to the minus ik dot r. So very much like the derivation in Once and Zenica, we do the same arguments in here, right? So I take delta Fm. Delta Fm is written in terms of psi k, as you know, delta Fm, as we wrote down before in the last lecture, that's equal to 1/2 summation of k. Remember this A plus kappa k square times psi k square. Remember that we wrote down. This A is second derivative of the free energy. As you know, A is equal to 1 over n1. Say in this case, say phi, first component, plus 1 over n2, 1 minus phi, minus 2 chi. Remember, we wrote that. In other words, this A, we wrote down to be A is equal to 2 chi s minus chi, going back to our previous lectures. Then we wrote down this to be equal to T minus, this is equal to T minus the TS by TS, TST if you like. And that's what we wrote down. So TS becomes a TC at the critical point, but in general, at the spinodal curve, that's the temperature. So that's the distance of temperature, right, from TS. Going back to this figure again, here was the temperature. Suppose I quench it here, or TC. This is the temperature. This is my critical temperature. That's a T minus TC, or T minus TS. That is portrayed by capital A, right? In addition to determination of molecular weight, chi parameter, et cetera, the distance in temperature from the spinodal curve is given by this capital A, right? Okay, so now we are equipped with everything that we need to do, right? How do you do this? So I have this expression, I have delta Fm, and I can take the derivative of delta Fm with respect to psi, right? Because phi is related to psi. I can take the derivative of this one with respect to psi and put that back in for mu, put it in here, and do the combinations of these things, right? If you do that, you get a very simple expression. Just to do it, if you do this, the expression that you get is the following. D by dt psi kt is equal to, right? That's equal to, that's equal to, right? A minus lambda k square. Lambda k square. The delta of delta psi k and delta Fm. Okay. How do I say this? Let me, maybe I should explain this, right? See, I have a phi, right? And phi is equal to, I'm writing phi is equal to some constant, which doesn't depend upon temperature, time, right? When I take the derivative of this with respect to time, this does not contribute. Therefore, I get only this one, d psi by dt. So that's that term. D phi by dt is d psi by dt. Then I have a minus sign, that becomes plus, and I get lambda. And then Fourier transform gradient is ik, right? I define my Fourier transform in here, and I take the derivative of this, I'll pick an ik here, or minus ik if you want. And then I have another derivative, therefore minus ik squared, that will give me, right, negative k squared. So here minus times minus is plus, and then I get negative k squared. So lambda k squared, and then this mu is a delta Fm by delta phi. Delta phi is a delta psi. So that's all I have written. So minus a lambda k squared, delta psi k in the denominator, delta Fm. And delta Fm, I know is this guy. This is quadratic in psi. So I take the derivative of delta Fm with respect to psi. When I do that, this factor of with respect to 1 psi k, the factor of 2 will kill this factor of 2. So I'll simply get a plus kappa k squared times psi k. So this is equal to minus lambda k squared a plus kappa k squared times psi k. This is a beautiful result. Right? Time evolution of psi kt is proportional to psi kt, ignoring all the terms in the nonlinear terms, right? All the terms. We took only the quadratic term, the Taylor series. We ignore all other terms. When you do that, you get this one. And please notice what is A. A is given by this quantity. When I go to the quench into the unstable state, when I go in here, this is my Tc. But the temperature here is below Tc. Or if I do to the off quench, this is Ts. The temperature here is below Ts, right? That means for our case, in this particular case, A is negative. A, right, is negative because T is less than Ts or Tc. Therefore, if this is less than this, A is negative. Therefore, this quantity for our particular situation, this is the negative quantity. We'll use this result. Now, how do I solve this equation? And that's easy to do because, you know, if I have, please remember, dy by dt is equal to, say, something like omega times y. That's what I have. Y is the psi kt, dy by dt, and psi kt is y. This whole thing is my omega. This whole thing is omega. Omega, since it depends on k, I write it as omega k. Therefore, in a solution of this one is, you know that y is equal to e to the omega t. At y at the t is equal to 0. You know the solution of this, right? Take the derivative of this, you get omega times this quantity, which is same as y, so you satisfy this quantity. All right? Okay. So I'm going to, since you know this, I'm not going to write this. There's no need for you to know this. So the solution of this then is psi kt is equal to psi k at 0 times e to the omega k times t. That's the solution of that equation. Okay. So what does that mean? Let's go and make measurements. I measure scattered intensity when I phase separate. I quench the system. I measure scattered intensity I of kt. Okay, that's equal to, as you know, is square of psi of kt square average. That's equal to psi of k at an earlier time, t is equal to 0 square average times e to the 2 omega kt. So it means it's exponentially growing. The intensity is growing exponentially with the time, right? But exponentially growing or decaying, we do not know. Whether it grows or decays, fluctuation grows or decays, we do not know. That depends upon this omega k. What is omega k? Omega k has these quantities, minus a mobility term, diffusion coefficient like term, lambda k squared times the square bracket, where here a is negative. Let's try to understand what this is going to be about. How does it depend on it, right? So let's do a very simple analysis. So omega k is equal to negative lambda k squared a k squared plus the interfacial term kappa k squared. I made a mistake. A plus kappa k squared times, did I write it correctly? Yeah. Kappa k squared. That's it. That's my rate. omega k is rate. See that here is the time. The prefactor of time is a rate. Rate times time is dimensionless, right? So it's a rate. So that rate is a lambda k squared times a plus kappa k squared. That's what we have here. Okay, let's try to plot this. Remember, right, a is negative. You know that, right? Remember, a is negative for phase separation. Therefore, if I want to plot this one, omega k as a function of k, because it depends on k. Let's do this. And this is a positive value. Rate is positive. Rate is negative here. So nothing happens here. Let's look at when k is equal to 0. K is equal to 0 there. That term goes away. Here is k. K is equal to 0. The whole thing goes away. At k is equal to 0, I have this point. When k is small, I have k squared here. That's quadratic. When k is small, this is negligible in comparison with the a. So the leading term would be the first term, a times negative lambda k squared. But a is negative. Remember, a is negative. If a is negative, this is negative, that's positive, quadratic. So this is going to go like this, quadratic, for small k. But let's look at what happens in the large k. For large k, right, this is k squared. This is going to be more important than a. So this is k squared. This parenthesis term is going to be dominated by k squared. So this is large. If this is large, I'm going to multiply. This is positive. Interfacial tension is positive. So I will have kappa k squared times k squared. That is k to the 4, kappa k to the 4. And then lambda is positive, but I have a negative sign. So this omega k will become negative, but k to the 4 very strongly. So it is going to come down like this. It's going to come down very strongly for larger k. So the shape of that curve is going to look like that. That's the way it's going to look like. So this stability analysis shows us there is a critical value of here, k critical, below which the fluctuation will grow because this is positive, right? This is above this horizontal axis, this is positive. For scattering wave vectors less than k critical, fluctuations will grow. For scattering wave vectors larger than kc, right, fluctuations will decay because it's negative. Now you also know k is scattering wave vector reciprocal of length scale, characteristic length scale. When I say k is smaller than kc, that means I'm talking about large wavelengths of fluctuations. When I talk about k larger than kc, I'm talking about short wavelengths. So what this picture shows is larger wavelength of fluctuations are growing and a smaller wavelength of fluctuations are decaying. So this is the bigger fluctuations are eating up, cannibalizing smaller fluctuations. They are growing at the cost of smaller fluctuations. The bigger fluctuations are growing. Now, what is the value of kc? That's easy to figure out. That kc is when this omega k is 0. When kc is at what value of k, omega k is going to be 0. One value is when k is equal to 0, it will be 0, of course, that's this number. And then when the square bracket becomes a 0, then I'll have this one. That is given by kc is given by, critical value is given by, as you can tell, kc squared is equal to, right, negative a by kappa, because this bracket is going to be 0, so kc squared is negative a by kappa, but a is negative already. Therefore, I'll write this to be a modulus by kappa. All right. Therefore, k critical goes like kappa square root, and we know what a is. We just worked it out. A is t minus ts. When a t is less than ts, is negative a, but if you put modulus, it's a ts minus t, right? Therefore, this one is ts minus t modulus. It's already, when I put Ts minus T, it's already positive, but to just ensure that we don't confuse the sign, I write it as a Ts minus T, square root. So the critical value of the fluctuation, critical wave vector, below which fluctuation will grow, is dictated by the quench depth. Okay, that's the formula. You know what A is. From Olsen-Zenica description, you know what A is. So from there, you can figure this out. Now the question is, what is the maximum at which the rate is going to be a maximum? What value of Km this is going to be maximum? And then also you can figure. Hello?
Hello?
Yes. For some reason, it was interrupted for a few minutes. Let me share the screen once more. Yeah. So what I was trying to say is, right, the rate is a positive for wave vectors, scattering wave vectors less than K critical. And then the rate is maximum at the value of Km. And you can determine the value of Km by looking for the condition where this is the maximum. That you get by taking the derivative of omega K with respect to K and equate that to 0. The derivative is equal to 0. That will give you Km. If that itself is equal to 0, that gives me Kc. When you take the derivative of this and do it, you can show that the Km is equal to 1 over square root of 2 times Kc. Okay. Okay. So what does that mean? And this means that if I take this expression and put it in my scattering wave vector K, I of Kt, right? And this is going to exponentially grow with time. The intensity is going to grow with the time for wave vectors which are shorter than omega K is positive, it will grow, right? Intensity is going to grow positive, right? Therefore, it will grow with the time. For wave vectors K, which is smaller than Kc, as long as it's smaller than Kc. But again, with all values of K below Kc, at Km, intensity will be maximum, right? So therefore, I can plot this as a function of, suppose I take I of Kt as a function of K. What will happen is it will grow like this. For beyond K critical, nothing will happen. There is no growth. There will be a cutoff. And then this will become like this. It will become like this. That's what we are saying. The intensity is going to grow with the time. This is T1, T2, T3. T3 is larger than T2. The intensity grows exponentially. Okay. At the same time, the K max is the same. It's not changing. That means at T1, suppose I had fluctuation like this. This is my lambda. This is for T1. And when I go to longer times, the fluctuation become bigger, but the wavelength, it doesn't change. Right? This is still lambda, same lambda. Right? The K max does not shift. But on the other hand, if you wait long enough, what will happen is, right? If you wait long enough, I of Kt versus K, right? Earlier on, it goes like this. Then eventually shift it to lower values of K because of the nonlinear terms, which we did not account for in Olsen-Zenica theory, right? We did only the second derivative of free energy. If we include the third derivative, fourth derivative, then the K max shifts like this. Okay, K max, right? Moves in that direction. This is my K max. Okay. Now that means, what does that mean? That means that the fluctuations, right? If I take the fluctuation to begin with, it will be like this. Then I have, right, very strong fluctuations like that. So here now, this is my lambda 2, and here it's only lambda 1. This is for T1, this is T2. The fluctuation wavelength becomes very large. That means K becomes small. That means bigger droplets are being formed, bigger domains are being formed. So what I can do is, suppose I plot logarithm of K maximum versus a logarithm of time, you'll see this is a yearly regime where it does not change. Remember, this one does not change at all. This is very early times. When the nonlinear effects come in, this will coarsen like this. And one can show that here your slope is 1/3, and here the slope is 1, -1, here -1/3. Okay. So that's the discussion of the spinodal decomposition. Now I'll show you some experimental data, how this works. Here. This is the data from some time back for a polymer blend, polystyrene polyvinyl methyl ether. And then please look at this. These are the early times, right? The quench depth is 1.8 degrees Celsius for this system. I have given the references, one reference there, another reference here. Please go and read it if you are interested in this topic. And please look at it for early times, right? 15.2 minutes and 59.3, up to say 39 minutes. And nothing happens. The peak position, 44, the peak position does not shift. But for the little later times, it shifts towards the left. K max shifts towards left. And here, look at this, 837, K max moved that far. Same condition, same system, same quench depth. When you wait longer and longer, K max moves towards left. And based upon this data, they have put a K max. In their paper, they use Q, I use K for scattering wave vector. Q max as a function of time, reduced to time, right? There's a time log plot, as you see. Here is the early regime, and then there's the intermediate regime, and that's the late regime. Okay, and the intermediate regime is called Lifshitz-Sliasov regime, condensation evaporation mechanism, which we'll talk about it later on, probably in the next lecture. And also there's a negative one regime, it's called CGR regime. It's dominated by hydrodynamics. So that's the general picture of how the phase separation takes place, according to spinodal decomposition mechanism. Okay. So according to the spinodal decomposition mechanism, the way first we have simple fluctuations, and they grow, eventually make the phase separated situation. And we have described with the paper and pencil about how to understand the fluctuations, right? And very simple arguments. And based on this, we are making predictions in the early stage. And for later stages, the theory becomes complicated, but it's doable. And that's the general picture. And that is validated completely by experimental measurements. For many, many systems, here I'm giving only one example. And I think I'm going to stop sharing the screen, and we can talk more. If you have any questions, we can talk more.